Hello, everyone, and thank you for being here. We're excited to present our Capstone project, Early Warning System, Predicting Graduation Risk in California Public Schools. Our work focuses on how districts can use publicly available data to identify schools at risk of low graduation outcomes without relying on protected student-level information. We'll walk through the challenges, the strategies we used, and the key results we uncovered. My name is Amayrani Balbuena, and presenting with me are Jun Clemente and Tanya Ortega. We're excited to share our findings with you. Here's an overview of the structure for today's presentation. We'll begin with the introduction and background, followed by a problem statement. Then we'll walk through our data source and exploratory analysis before outlining our modeling approach. After that, we'll cover our key results, discuss the implications, and conclude with the next steps. We'll start by explaining the real-world importance of the challenges we're addressing. Graduation outcomes have a major influence on students' long-term academic and economic opportunities. In California, the statewide graduation rate is about 87%, but several student groups and districts continue to fall below the 80% mark. That means that statewide average masks significant disparities. Because of this, districts need accessible tools that help identify risk early, not after students have already fallen behind. Our project aims to provide exactly that by developing a scalable early warning approach using only publicly available school-level data. Before we get into our approach, we want to clarify the challenges that districts face today. Most existing early warning systems depend on detailed student-level data, things like absences, grades, and behavior. But all of this information is protected under the Family Educational Rights and Privacy Act, or FERPA, which limits districts' ability to share or model student-level data at scale. As a result, many schools, especially smaller districts, lack transparent and easily accessible early warning tools. This led us to our core question: can publicly available school-level data reliably identify at-risk schools? There's very limited research on school-level predictors of graduation risk, so our project explores whether we can build a FERPA-compliant, statewide scalable system that predicts which schools fall below the 90% graduation threshold. To answer this question, we organized our project around four main objectives. First, we identified indicators by gathering and exploring data sets from the California Department of Education, looking for variables that might relate to graduation outcomes. Second, we analyzed these indicators to determine which ones actually act as meaningful predictors. Third, we built and compared multiple models to classify whether a school is likely to fall below the 90% graduation rate. This included testing linear models, tree-based models, and probabilistic classifiers. And finally, we developed insights and visualizations that can help districts and policymakers make more informed decisions. Together, these objectives guided the full life cycle of our projects, from data collection to modeling to interpretation.
Thank you, Amayrani. My name is Jun Clemente, and I'll start by introducing our primary data sources. For this project, we pulled multiple publicly available data sets from the California Department of Education, focusing on the 2021 to 2022 academic year. The most important data set is the Adjusted Cohort Graduation Rate, or ACGR, which provides the official graduation outcomes we're predicting. We also incorporated chronic absenteeism data and absenteeism by reason, which gave us detailed indicators around student attendance. To build out the school level context, we added the school directory dataset, which includes enrollment and school characteristics, and the FRPM dataset, which helped us capture socioeconomic indicators. All of these datasets together form the foundation for our school level early warning system. Next, we expanded our dataset using staff related data from the CDE. We included certificated staff assignments, student staff ratios, and multiple staff qualifications datasets, such as years of experience and degree attainment. We also added enrollment data so we could calculate school level ratios and contextual metrics. These staff and demographic indicators allowed us to capture the support and services portion of the ABC framework. In addition to CDE data, we pulled school climate and connectedness indicators from the Cal SCHLS survey. This dataset provides perception-based safety and support metrics, such as students feeling safe at school or connected to adults on campus. However, the challenge here was that the data were only available at the county level, not the school level, which limited how precisely we could use behavior related features. We still included it to give the model a broader context around school environment and climate. To manage all of these sources, we built an end to end ETL pipeline in Python. In the extract phase, we loaded 12 public datasets into pandas data frames. In the transform step, we applied a consistent filtering strategy. We kept only school level records, removed charter and DASS schools, and focused on the TA reporting category, which provided total values for each school. We also cleaned column names and standardized formats across datasets. In the load step, we saved each cleaned and filtered dataset as a pickle file so it could be reused throughout our notebooks without reprocessing. This setup made the entire workflow reproducible and much more efficient. After cleaning each dataset individually, we merged them using the Common School Identifier, the CDS code. This created a unified school level dataset. At this stage, we also removed rows where the cohort reporting was suppressed or incomplete. For example, schools where fewer than 90% of students had reported graduation outcomes. We also restricted the dataset to traditional high schools to keep the population consistent. Because the CalS CHLS climate data were at the county level, we aligned those values to schools based on county code. After all preparation steps, we ended up with two modeling datasets, a version with climate features, which included 958 schools, and a version without climate features, which included 806 schools. Next, we conducted exploratory data analysis beginning with univariate distributions. One of the first things we noticed was that graduation rate is left skewed. Most schools are clustered between 90 and 100%, with fewer schools at lower rates. We also saw a strong class imbalance. Only about 26% of schools fell into the at risk category. Most missingness in our dataset was structural, meaning entire variables were missing because they weren't collected for certain schools. The climate data also showed inconsistencies across counties, which helped explain why behavior related features had weaker signal later on. Finally, several predictors like chronic absenteeism and FRPM were right skewed, which guided how we approached feature engineering. Then we looked at how each feature related to graduation outcomes. Starting with attendance, chronic absenteeism and unexcused absences showed clear negative relationships with graduation rate. You can see in the scatter plot that as absenteeism increases, graduation rates tend to decline. This strongly aligns with the A in the ABC framework. For behavior, we expected similar trends, but because the climate and connectedness indicators were available only at the county level, the signal wasn't as strong or consistent. On the positive side, AG completion, which reflects course performance, had one of the strongest positive correlations with graduation rate. Teacher experience also showed a meaningful positive association. We did see a slight positive correlation with student teacher ratio, which was unexpected and worth further exploration. These insights helped us identify which predictors were likely to matter most during modeling. Based on our EDA results, we performed several feature engineering steps to make the dataset model ready. Under feature removal, we dropped low variance connectedness variables and categorical features that didn't provide meaningful differentiation. Under feature transformation, we converted the Likert scale safety indicators into a weighted score and created an average safety score to summarize the climate dimension. All numerical standardization was handled inside the model pipeline. Finally, under target engineering, we created a binary outcome variable. Schools with graduation rates below 90% were labeled at risk, and schools at or above 90% were labeled on track. These engineered features produced a cleaner, more predictive data set to feed into the modeling phase.
Hello, everyone. This is Tanya speaking. I'll be presenting the modeling approach. For this project, our goal was to figure out which machine learning model could best identify schools at risk for low graduation rates using only school level public data. So we compared a diverse set of algorithms for simpler models like logistic regression to more flexible ones like random forest, XGBoost, and SVM. Testing variety of models allow us to see whether more complex models actually improve prediction in this context. For training, we use the 80-20 stratified split to keep the natural class in balance, and we apply class-weighted training instead of oversampling to avoid distorting the data. Standardization was built into the pipeline as well. Because accuracy alone can be misleading with imbalance, we focus on precision, recall, and F1, and especially PR-OC. These metrics help us understand not just how well a model performs overall, but how reliable it can detect the schools that need the most attention. Next, we have top predictors. These are the top predictors that have the strongest influence on whether a school was labeled at risk. What we see here reflects well-known patterns in education research. Still enrolled rate and chronic absence were the biggest drivers, showing how attendance directly affects the school ability to support students to graduation. Unexcused absences and FRPM eligibility highlight the impact of socioeconomic barriers. A through G completion captures academic readiness, and factors like suspension rates and teacher experience speak to school climate and stability. What's important is that all of these predictors come from publicly available school level data, yet they mirror the same signals used in traditional school level early warning systems. Let's move forward to model performance. This slide shows how each of the 7 models performed using PR-OC, which is the most reliable metric for imbalanced data like ours. What we see here is that Random Forest stands out with the highest PR-OC score of about 0.77, meaning it is the most effective at identifying schools that were truly at risk. Logistic regression and naive Bayes also perform well and show more stable recall, which is important because recall tells how many at-risk schools the model actually catches. XGBoost performed reasonably, but didn't outperform Random Forest in this context. On the lower end, SVM and KN struggled. SVM had the perfect precision but extremely poor recall, meaning it identified almost no actual at-risk schools. And KNN had overall weak performance. Overall, this comparison helps us confirm that Random Forest provides the best balance of precision and recall for detecting schools with lower than expected graduation rates. Key insights and discussion. These findings give us a clear picture of what drives lower graduation rates at the school level. Attendance indicators, especially chronic absences, were the strongest predictors, showing how engagement and presence in school directly affect graduation outcomes. Socioeconomic disadvantage reflected through FRPM eligibility was also heavily linked to risk, reinforcing long-standing equity concerns in public education. Academic readiness measured through A through G completion continues to be a key factor, and teacher experience adds an important piece related to school climate and stability. What is meaningful here is that these predictors align with the ABC framework and national dropout research, which typically rely on student-level data. Overall, our results will show that even with school-level public data, we can approximate many of the same risk patterns even in traditional early warning system, making this approach both scalable and accessible for districts with limited data capacity.
These are the main limitations that shaped our analysis. First, school climate and safety indicators for 2021 to 2022 weren't publicly available, so we weren't able to include those behavioral or perception-based measures. Our data set also represents a single year, which means the model reflects one snapshot in time rather than long-term patterns. Another limitation is granularity. Because we relied on school-level aggregates, we can't identify variations within schools or individual student risk. Data availability was also inconsistent. Some potentially meaningful indicators, like counseling ratios or intervention programs, are not reported statewide. And finally, states differ widely in the indicators they publish, which limits generalization without adjusting the feature set. These constraints help clarify what the model can and cannot do within the scope of the publicly available data. To wrap up, our results show that public school level data can reliably identify schools at risk of low graduation rates. Attendance measures, socioeconomic disadvantages, A through G completion, and teacher experience consistently emerged as the strongest predictors. Among all the models we tested, Random Forest delivered the most balanced performance, making it the best option for early identification. Because our approach uses only publicly available data, it's fully FERPA compliant and scalable across districts and states. And importantly, our findings mirror well-established dropout patterns in existing research, which supports the validity of our model. For future development, we recommend incorporating updated climate survey data once the state releases it. Additional support indicators, such as counseling ratios or mental health resources, would also strengthen the model's performance. A multi-year modeling approach would capture longitudinal trends and improve generalizability. And finally, this framework can be adapted for other states, but the specific features would need to be adjusted depending on what indicators each state reports. The modeling pipeline remains the same. The inputs would change. Thank you for your attention and for taking the time to engage with our project. We hope our work contributes to ongoing efforts to better support students and schools through data-driven insights. We're happy to answer any questions you may have.